In this video, I show you how you can find cyclic dependencies in your C# code. I use a tool I named C# Code Analyst, and a GitHub repository link to the tool can be found in the video description. So why should you care about cyclic dependencies at all? Because cyclic code structures make your code often more difficult to read, maintain, and test. Now, just because you have a tool that reveals the cycles in your code does not mean you have to remove them. Some cycles just don't matter, some may even be intentional, so the goal here is to be aware of them and then you can decide. A good advice to start with is to keep at least your namespaces free of cycles. So let's begin. To show you how the tool works, I just import an arbitrary C# solution file. So the C# Code Analyst tool now creates a dependency graph from your code base. External code is not imported, however. So once this is finished, we can click the Find Cycles button, and the application now searches for so-called strongly connected components in your code graph. These are clusters of code where everything is connected. So this is quite fast, and we are already done. The result is shown here in a summary table, and this summary table shows you at which level this cycle occurs and how many code elements there are involved. Here we find the levels other, type, and namespace. Others are actually just cycles at a method level, and I added this out of curiosity to see the recursive method calls in my code base. By right-clicking a line in the summary table, you can copy the related code elements to a code graph where we can analyze them. As mentioned, here you can see the recursive method calls. The color assigned to methods is blue. If you want to see the classes where the method belongs to, you can use the context menu in the free space around the graph, and you click Complete to containing types. Here in this example, everything is located in a single class, and the color assigned to classes is yellow. And if you want to include the next parent container, click in the context menu, Add Parent. So, and now the namespace is added. The color assigned to namespaces is turquoise, and these are actually all colors that you need to know in this video. So let's go back to the summary and see some more interesting things. So next I choose a cycle at a class or type level. So here we have one, and this is a cycle between two classes that involves 14 code elements. So I again use the context menu to move this cycle to the graph view. And here we can see the two yellow classes that depend on each other. Here is something important to note. When we have a large amount of code elements in the graph, everything gets quite slow. About 100 elements are perfectly fine. That is the reason when you open a cycle, everything is collapsed. The dependency arrows are merged and the numbers tell you how much dependencies there are. This 4 here means that there are 4 dependencies from the tab manager somewhere inside the main view model. This limitation to the code elements that we can handle in the graph is actually not a real limitation. If you have more than 100 code elements in a graph, you can't make sense of it anyway. That's too much information. But for larger cycle groups, we need a strategy. And I explain this when we look at the cycles at the namespace level. For now, there are 14 code elements involved. This is not too much, so I can expand everything. By default, there is a highlighting active that just highlights the edges you hover over. So this here. Another possible highlighting is outgoing edges. This highlights all outgoing edges somewhere inside the hovered code element. If I hover over the method show hierarchical data, then you can see two outgoing edges. So this means show hierarchical data calls into the methods show hierarchical data as treemap and show hierarchical data as circle packaging. If I hover over the class main view model itself, you can see the outgoing edges of all children. So just from the names here, we can see that the view model asks the tab manager to open or show a certain tab. But when we hover over the tab manager, we see that the tabs itself and the selected index are actually located in the view model. So if I would remove this cycle, I would likely start to move the tabs and the selected index to the tab manager. In this simple example, we can also see why cyclic dependencies make it often more difficult to understand code. The cycle causes the two classes to be treated as one unit. If we want to make changes in one of these classes, we likely have to read and understand the code of the other two. Such an example, by the way, often occurs if you have coding guidelines in the form a class must not have more than X lines of code. So it's easy to fulfill this guideline simply by splitting larger classes into two smaller ones. But actually not much is improved here. Due to the cycle, you still have to treat both classes as if they are a single one, but your metrics actually are fine. Let's go back to the summary page and look at some namespace cycles. So here I choose a namespace cycle that involves two namespaces, and there are 44 code elements involved. Here we see an expanded namespace called GitProvider with everything else inside. So where is the cycle here? There is an inner namespace called debugging, and classes from the outer namespace use things from the inner debugging namespace. On the other side, the inner debugging namespace uses things from the outer namespace, which seems actually be only data structures, and I assume it dumps these data structures to a file or something like this. I added this example only to show you how dependencies to inner namespaces are presented in this tool. In this example, I would not remove the cycle. If I add the inheritance tree to the class GitProvider, to this image, you can see that it implements an interface iSource control provider. And this interface is the only contract to the outside world of this package. So everything else is nicely encapsulated inside the GitProvider namespace, and nothing else on the screen is revealed to the outside. That looks all good to me, and I would not waste any energy to remove this cycle. I don't see any benefits here. If again I show the inheritance tree for the iSource control provider interface, we can actually see that there is another implementation for Subversion. So let's look at the last example at the namespace level. And I think this is also the most interesting one. So I choose this cycle here that involves 3 namespaces and has 25 code elements in it. So this cycle group is quite small. In a larger application, you can easily have cycle groups with many namespaces and hundreds and even thousands involved code elements. So we need a strategy how to resolve this piece by piece. So let's assume this here is one of these larger cycle groups. How would we proceed? First, I would choose another highlighting. This is the shortest non-self circuit. If I hover now over a node, it highlights the shorted path back to itself. Loops to itself are excluded, of course, so everything in this group is connected to each other. Select any two nodes and there is a path between them. With this highlighting, I can see that there are actually two elementary cycles in this larger group. It's all easy to see in this small example, but if the code is larger, it's not so clear and the highlighting is very helpful. So how would we proceed? Just the fact that we can see a namespace called interface that depends on a tool or common namespace seems just wrong. So we have to fix this. I decide to investigate the cycle between interfaces and tools first, just because the dependency from interfaces to tool is just a single dependency. So I want to remove everything else from the screen, and this reduces the amount of information I have to deal with. To do so, I hold the Control key and click on the namespaces I'm interested in, which is tools and interfaces. Then I click again in the free space around the graph, and then I select Marked Focus, and this removes everything else from the screen and focuses just on the two interfaces I'm interested in. Now I can expand the namespaces and look inside. And also choose, again, outgoing edges as highlighting. So if I hover over interfaces, I can see the single outgoing edge. And we see that the only dependency from interfaces to tool is a dependency from iRenderer to iHighlighting. So let's look what this actually is. Click Control and then on the iRenderer. This holds the yellow quick info fixed to iRenderer, and you can click the hyperlink to open the iRenderer in a text editor. Here we can see that the iRenderer needs the iHighlighting interface as the type of a property. And here it's already clear that the iHighlighting should be part of the interface package itself and should be moved there. So that's how we would use the tool to analyze cycles. We start with a smaller cycle or dependencies that don't make sense for us. We remove everything else on the screen and then dig into it to understand where the cycle comes from. We remove the cycle and repeat. This procedure works also for larger cyclic code clusters. So that was a short introduction how the C Code Analyst tool can be used to find cycles in your code. Before we end this video, I want to give you one advice. I assume that you already know that you can break any cycle by just introducing an interface. However, do not do this mindlessly. First, decide if you want to remove the cycle at all, and then think about how to solve it. Just adding an interface may not be a good solution. We already seen in the examples that some cycles may be solved just by moving interfaces or methods where they actually belong. So let's look at this example here. There are two classes, A and B, and they depend on each other. You could get rid of the source code or compile time dependency just by adding an interface as shown here in the middle. Or you could take a deeper look and maybe find that class B has too much responsibilities in the first place. Then you could split class B into two parts such that B1 depends on A and A depends on B2 as shown here in the lower part of the image. While the first approach just hides the dependencies, the second one is a real improvement to your code base. I asked Claude AI one of these large language models to create an example, and it came up with the following code. In this code example, there is a class user and there is a class order. And both form a cycle. The order class has a method is eligible for discount, and to answer this question, it needs the user, while the user has a list of orders. Now, adding an interface would not improve this code at all. Yes, the compile time dependencies are gone, but both classes are still entangled in each other, and you kind of just mask or hide the dependencies. That's not how you would improve the maintainability of your code base. Let's see what Claude AI suggested as a solution for this problem. So the order class became now a simple order detail data class, and the decision if the customer is eligible for a discount is moved to a new customer loyalty class. Now, an order service could use this code and, for example, get a user from a repository, get the orders from the user, and use the new customer loyalty class to ask for the is eligible for discount. And this gives a nice hierarchical structure without any cycles. And I agree that this is a real improvement over just adding an interface.